So my name is Kenny Quintana, and I'm going to be going over some environmental engineering problems today. These problems come from Mackenzie L. Davis's Intro to Environmental Engineering book. So let's just hop into the first question. 1-3. A residential development of 280 houses is being planned. Assume that the American Water Works Association average daily household consumption applies and that each house has 3 residents. Estimate the additional average daily water production in liters per day that will have to be supplied to the city. So let's just define some variables real quick. The number of houses in this development is 280. And the average daily household consumption, I'll use Q because it's in volume per time. So Q average, and then this number is 1,000 liters per day. It comes from the book, and it comes from AWA, WWA. So let's just find the total demand that the city needs to produce. 280 houses, 1,000 liters per day per house. Liters per day. And that's going to be just about 280,000 liters per day. That was a pretty quick question, so let's move on to the next one. Okay. 1-4, repeat problem 1-3 for 320 houses, but assume that low flush valves reduce water consumption by 14%. So we have 320. Our number of houses is 320. And our average demand is still 1,000 liters per day, but we're going to have a reduced demand because of these. Just like to add that equal sign because of these low flush valves. So that's going to be our average demand times 1 minus 0.14. The 1 is 100%, 0.14, 14%. So 860 liters per day. And so our Q total is going to be the same thing as last time. It's going to be the demand at each house multiplied by the number of houses, liters per day. This demand is 275,000, a little less than 1-3, but we got 40 more houses in this development. So we can see that reducing water consumption by even just 14% has a huge effect on the amount of water that a city is able to supply to help grow. So let's move on to 1-5. Using the data in problem 1-3 and assuming that the houses are metered, determine what additional demand will be made at the peak hour. So also from the book, our peak factor for the max hour is 5.3. And then our Q average is going to be, we hop back to 1-3, 280,000 liters per day. And so our Q peak is going to be our average hourly demand multiplied by the peak factor. So during that peak hour, the city will need to supply about 1.5 million liters per day. And so this just shows that, a city doesn't always supply, a steady demand. It fluctuates throughout the day. So we need storage tanks and other systems in place to account for, human nature, and we don't use water at a perfectly constant rate. Okay, this last question. The American Water Works Association estimates that 15% of the water that utilities process is lost each day. Assuming that the loss was from public supply withdrawal in 2000, estimate the total value of lost water if delivered water costs $0.45 per cubic meter. Okay, so problem 1-2 has a little table with the year, population, and public supply withdrawal. So in the year 2000, the Q withdrawal is 1.64 times 10 to the 8th meters cubed per day. So if 15% of that water lost, let's take the total withdrawn, 0.15. That gives us around 2 million, right? A lot of zeros now, 24 million cubic meters per day. And so let's get our dollars lost. And if we know we have this volume of water lost each day, and we know the value of each cubic meter, we just need to multiply that volume by the price. And let me turn this into dollars real quick. Okay, per day. So each day, about $11 million are lost just due to processing water. So as environmental engineers, with sustainability as our goal, we can work to eliminate these losses and save everybody money and help use the money to fund other projects. So that kind of gives you an idea for some environmental systems. These were all water systems. They're probably we're most familiar with those, from fluid mechanics, hydraulics. So next week, or not next week, next video, we'll talk about materials balances, energy balances, thermodynamics, kind of help us measure where pollutants are within these systems. So thank you guys for watching, and I'll see you in the next video.